What I want to do first today is give you an interesting discussion of a strange quirk with the parallel streams use of the flatMap intermediate operation. So as you're probably all familiar with, flatMap is an operation that's available in streams that takes a stream, which is typically nested. So you might have a stream of streams, you might have a stream of lists or something like that. And it goes ahead and it flattens it. So you end up with a stream of whatevers. So you might have a stream of lists of integer and it'll turn into a stream of integer by doing flatMap. And flatMap works very nicely and very conveniently for sequential programs, but it has a really weird quirk with parallel programs. So what I'm going to do now is I'm going to show you an example code snippet or an example from my GitHub repository that will demonstrate this problem, and then I'll show you how to fix it so you can get the benefits of flatMap semantics without having to deal with the quirks of flatMap's non-scalability for parallel programs. And we'll see how you can fix it by using a combination of the reduce terminal operation and something called Stream.concat. So here's the program. This is my EX35 program. I will upload a video that will point you to the link where you can get the code for this. So it'll all be available on my, it'll be available on the course website and my YouTube playlist. So here's the main entry point into the test program. We are going to run a test that will test the flatMap example, show what's wrong with it. And then we're going to run another test that shows how to fix that with a combination of reduce and Stream.concat. And when we're done, we're going to print the timing results, which will demonstrate in terms of the performance, which one runs better, which takes better advantage of parallelism. And then we'll also take a look at some output that will also conclusively demonstrate what the problems are with the flatMap implementation. The run test method is a clever little helper method that I use a lot in my tests. As you can see, what it does is it takes a runnable, which will be the method to call, it'll be a method reference, and the name of the test, and it first garbage collects so that everybody can start off on a level playing field. And then we use this method called timeRun, which is part of the run timer class. And timeRun, as you can see, starts the timer, runs the run method on the runnable, stops the timer, and then inserts the execution time that's computed by starting and stopping the timer into a result map with a given test name. So that way we can get the results later when we need them, as you'll see in a moment. So let's pop back up here and we'll look at the testFlatMap call first. So this is going to do some interesting things. The program is just kind of a silly program to demonstrate the issues. It's not particularly profound, but it's kind of fun to look at. So what we're going to do is we're first going to generate an outer stream for a certain number of iterations, and the iterations are what's provided by our options singleton, one of the few good examples of when to use a singleton, I think. And what we're then going to do, so let's take a look at generate outer stream. So generate outer stream is going to generate an int stream from 1 to the number of iterations, which could be, say, 5, so it'll be 1, 2, 3, 4, 5. And then it'll box those ints up into integers, so we now have a stream of integers. We now have a parallel stream of integers, and now we're going to go ahead and use the peak debugging operation. It's an intermediate operation that's used for debugging purposes or logging purposes, and we're going to indicate that the outer thread ID for this given number of iterations is going to be whatever the current thread ID is. And you'll see what those are when we print them out. They'll just be numbers. So that's what generate outer stream does. It basically returns a parallel stream that emits iteration numbers of integer objects. And then we take that, and then we call flatMap. And let's take a look and see what flatMap is going to do. So flatMap, as you know, is this intermediate operation that attempts to try to denest what it's given as its results. And we're going to give it a stream that comes back from Interstream. So here is Interstream. And as you can see, Interstream is going to return an Interstream that will emit a certain number of integer objects from 1 to the number of iterations that we passed it. And this method will also have a really cool debugging tool that will show that checks to see whether the Interstream actually runs in parallel or not. We would like it to run in parallel, but as you're going to see here, things don't always go our way. So here's the Interstream. We give it the iteration count here. and we're going to record the outer thread ID. That was the thread ID of the calling thread that we got when we came in here. And we then create a new atomic integer. We'll see why we do an atomic integer here in a second. We basically do this so we can pass it by reference, and you'll see why we need to do that. And then we create ourselves a concurrent hash map that maps longs, which are thread IDs, to the atomic integer. And we're going to see how that gets used. Then what we're going to do is we're going to make ourselves an inner stream that's going to go from 1 to the number of iterations. So it'll start out with 1 iteration, then 2 iterations, then 3 iterations, then 4 iterations, then 5 iterations, up to the number that is used by the outer stream. We box those ints into integers, and then we tell the stream, I would like you to please run in parallel. Now, you'll see in some circumstances that request is honored, in others, strangely, it is not. Even though you would like it to be, it is not always honored. And then what we're going to do is, once again, we're going to use the peek debugging hook in order to call this very clever method called check inner stream thread IDs. And I'll walk through that in a second. What it's going to do is it's going to check to see what thread IDs are actually used to run the computations. And the results may surprise you. So what we're then going to do is, notice how what we're doing here is we're returning a stream of integers from 1 to the parameter that's passed in here. And so that will come back as the call to flatMap. So if you think about what's happening here, inner stream, for every integer that we're going through in the outer stream, so that for every integer in the outer stream, which would be 1, then 2, then 3, then 4 or 5, whatever the count is, we're going to then use flatMap to call inner stream, and inner stream will return a stream. So of course you'll end up with a stream of streams, and flatMap will flatten them, so you'll end up with a stream of integers as opposed to a stream of integers. And we would like this to run in parallel, but we'll see things don't go our way. Then we go ahead and collect the results up into a list, and then we print the results. So that's what we're going to do for the testFlatMap call. Now let's pop back, and we'll take a look at testReduceConcat. So this is an alternative way of doing the same thing, except as we'll see when we run the test, it fixes this weird quirk / bug / intentional omission of optimization that could have been added but has not yet been added to Java. It fixes this problem in a very clever way. So how does it work? Well, first of all, it also generates an outer stream. So remember, for the number of iterations we're going to pass in. And if just a quick recap, the outer stream is going to generate a stream of integers from 1 to whatever the parameter is here. And it's going to have that be a parallel stream. Then what we're going to do here is we're going to, once again, use Interstream. But the difference is, this time, that the Interstream is going to be called by map instead of flatMap. If you recall before, we used flatMap here, so it would take the stream of streams and flatten them. But this time we're going to call map. What's the main difference between flatMap and map? Map always returns an output stream that has exactly the same number of elements as its input stream, whereas flatMap can flatten it. So you may end up with less or more, or the same, depending on what you're trying to do. So we're going to end up calling Interstream again. Just a quick recap of Interstream for completeness. Interstream is going to go ahead and generate this inner stream of integers from 1 to the number of iterations, which is passed in as a parameter. It's got this cool little thing called check Interstream thread IDs that we'll talk about in a second. And what you get back here will be a stream of streams of integers. In fact, if you take a look, you can see that IntelliJ is telling me the return value from this is a stream of integers. Well, we don't want a stream of integers. We want a stream of integers. And so what we do to get that is we use this clever little technique, it's an idiom, I suppose, where we take reduce, and we're going to take each of those streams of streams, and we're going to concatenate them together to form one complete stream. And that particular version of reduce actually is going to return an optional, because it could very well have nothing in it. So we're going to then have to use the or else method on optional to say, if for some reason there's nothing in the stream, then return an empty stream. We don't have that situation in this use case, but you have to prepare for it because it's possible, and that's why the API works that way. And then we go ahead and we collect the results. So what I'm going to do is I'm going to run the tests. You'll see the results, and then we'll go look at the clever little program that gives the results that we want to see. So a couple things. First, notice the difference in performance. testReduce.concat executes really quickly, something like 4 milliseconds, whereas testFlatMap executes much slower, 52 milliseconds. Why is that? Well, as you'll see, it's because testFlatMap actually doesn't run the inner stream in parallel. It only runs the outer stream in parallel. So it doesn't take advantage of my multitude of multi-core processors, or multi-cores on this particular processor. I've got 8 cores, 8 hyper-threaded cores, so it's even faster. So here's what happens. We enter the program with 16 cores available, and the first thing we're going to do is we're going to test flatMap. And you'll notice that we have the counts here where we're going to have the thread IDs, and you can see that we've got 22, 21, 20, and 1. And then what you can see we have here is the IDs and the inner thread IDs for the outer thread IDs. And I'll show you where we get these results in a second. And what's happening here, for example, here's the outer thread 21, which is this guy, and it's got a count of 5, right? So it's got 5 of these iterations. But all 5 iterations all run in the same thread, in thread 21. So there's no parallelism going on in the inner stream. The outer stream has parallelism, the inner stream does not. And that happens for each of these things. So you can see this is a count of the number of processing steps that are done in that given thread. So you can see for every case, the inner stream is running in the same thread as the outer stream, and all of the inner stream computations are being done in that same outer thread. And that's because flatMap doesn't work for parallel streams when shown in the way I'm using it here. It just doesn't scale. Conversely, and then the results, as you can see, are 1, 1, 2, 1, 2, 3, 1, 2, 3, 4, 1, 2, 3, 4, 5. That's what we get as the results. In contrast here, what you see is the following for the other test. And what's happening here is we once again have outer threads which have various numbers, but the inner threads are actually running in different thread IDs, meaning that they are running in parallel as well. So just for example, let's pick the one that has the most of these. So this is thread 20. So thread 20 is doing this inner stream iteration for 5 values. And as you can see, if you look at thread 20, its inner stream is running in, one of them's running in thread 21, 2 things run in thread 25, 1 runs in thread 28, another runs in thread 30. So what you can see here is that for the version that uses reduce and Stream.concat, the inner stream is running in parallel, but for the version that's running the flatMap version, the inner stream is running sequentially. And that, of course, explains why the results are so radically different. So let's go back just for kicks, because this is a really fun little thing I did. Let's go take a look at the method that I wrote that's called check inner stream thread IDs. And you can see it's given a count of the number of iterations we're doing, the counter, which is the atomic integer, the thread map, and the outer thread ID. So let's go ahead and take a look at check inner thread IDs. So this particular helper method is going to compute and print how many threads are being used to process the inner parallel stream. And this is what it does. This is super duper clever. So the first thing we do is we use our thread map, and we go and we say, have we seen this thread ID yet? Is this the first time that it's been encountered? And this uses something called put if absent. And what put if absent does is it'll either return the current value, which in this case is an atomic integer, or it will call this mapping function to initialize that key in the map. So keep in mind it's a concurrent hash map. It's got a key, which is the thread ID. It's got a value, which is the atomic integer that's keeping track of how many times that thread ID has appeared thus far. And so the first time in, we create an atomic integer with a value of 1, and we stick it in the map. When putIfAbsent is called, it'll either return null if this was the first time in, or it's going to call, or it's going to go ahead and return what's coming back from putIfAbsent, which would be the atomic integer that was previously there. So if the value is not null, we got back an atomic integer, in which case we increment its value by 1, which means that we've already seen this thread ID before, so we're reusing thread IDs. So for the case where flatMap was being used, if you come back over here, you can see that flatMap recycled that atomic integer for every single thread ID because it was always the same thread ID, so that count was just getting incremented every time it was called for every one of the elements. In contrast, for the one that's running reduce in Stream.concat, then as you can see, oftentimes you'll have different thread IDs being used. Sometimes they're the same if they're recycled, but most of the time they're different, which means that things are actually running in parallel. And so we're incrementing the count by 1, and then if the iteration that we have here, which is what is passed in, if the iteration or the count is equal to the max number of iterations, which is say 5 or 4 or 3, then we go ahead and we print out the results, indicating that the inner thread IDs for the outer thread ID equals whatever the map contains. And so that's the way to display the results, indicating whether or not parallelism is taking place. So that's really there just to show you a super duper clever way of being able to determine how things are working with respect to concurrency and parallelism. But the big picture view here is that if you use the approach that is based on reduce and Stream.concat, you get parallelism for inner streams, whereas if you use the approach that uses flatMap, you don't get parallelism for inner streams. And that's a very important thing to remember. And it also demonstrates that it's not always the case that Java parallel streams is just a complete minuscule set of changes to go from a sequential version to a parallel version. You have to take into account these kinds of weird implementation quirks. And this is indeed a weird implementation quirk. They could have done it a different way, but chose not to.